is not working. Now it's working, but it's not the right camera. So the camera I can change easily. Okay. Now it works. Good. Perfect. Sorry. You see me? It's okay? Okay. Okay. So the temperature, we said, measures the local agitation of molecules. Okay, of molecules. Okay, you know that when there is when you are not at the absolute zero, there is always some thermal agitation, and the temperature measures that. Whereas the heat encompasses all the kinetic energy of all the molecules in the system. Okay, so it's two very different things. The heat depends on the whole system, and if you double the system, you will double the heat it contains, whereas temperature is a local measurement at one point in the system. And then we saw one very important formula, which expresses how much heat you need if you want to heat up some mass m of some substance characterized by some value for the specific heat of a certain temperature difference from an initial temperature to a final temperature. Okay, and this guy here, we call it also delta T, the final temperature minus the initial temperature. And we explained why this formula has this form, because the heat is proportional to the quantity of matter, because the heat depends on the substance, and because the heat depends on how many degrees, by how many degrees you want to warm up or cool down the substance. So I remember that when Q is positive, it means that the final temperature is bigger than the initial temperature. And when Q is negative, it means that the final temperature is smaller than the initial temperature. So depending on the sign of Q, you know if you've been heating up the system or if you've been cooling it down. Okay? When you give energy to a system, Q is 0. When you receive energy from a system, Q is negative. Okay? Are you still there? Good. Sorry? Yeah. Okay, so I gave you two exercises to do, which were number 3 and 4, page 9. Okay. So why did I write the answer here? Yeah, because we warm up 500 grams of water from 20 to 80 as in the previous problem. So we had calculated that the quantity of heat we need for that is 125,400 joules. And now the question is, assuming that the power of the heating device is 800 watts, for how much time should it work, assuming an efficiency of 100%? So does somebody want to give the answer to that? Yeah. So you have that the energy is the power times the time. Okay. Be very careful here. You see the T's, use small t for time and big T for temperature. Otherwise it will be a mess. And so out of this formula, you extracted a formula for the time, which is the energy divided by the power. This is what you are telling me, right? Okay, and how much did you find? In seconds. 156 seconds. Let's say approximately 156 seconds. That will do it. 2 minutes and 36 seconds. Okay? Do the other things that's correct? Yeah, it's correct. Okay? So indeed, you need a certain quantity of energy to heat up the water. Your heating system provides you with 800 joules per second because this is watts and watts are joules per second. Okay, so you can compute how many seconds you need to obtain that energy. Okay, now we have the same question as in the previous exercise, but now we have an efficiency of 90%. Okay, so how should we change that? What is going to change? You know that the efficiency is the energy which is useful divided by the energy which is used. Okay, and which one do we need now? Which one do we know? Do we know the useful energy or do we know the used energy? What is fixed? What would you say? Yes, and the useful energy is given by which quantity here? The useful energy is the energy you are going to need to warm up the water. Okay, this is not going to change. It has nothing to do with the efficiency of your heating device. You need a certain quantity of energy to heat up the water. This is 125,400. And so if we want to compute the energy which is used, so the energy which is used is going to be the energy which is useful divided by eta. If you take this expression, it gives you E used times eta is E useful, and then you divide by eta on both sides, and you have this expression. Okay? And this expression works nicely because you divide by 0.9, so the energy which is used is going to be larger than the useful energy. Okay, so this is 125. Sorry, what did you say? Hello? Okay, so let's divide this 125,400. Let's divide it by 0.9. And this gives us 139,333, then it's periodic joules, okay? This is the energy we need if the heating system has an efficiency of 90% and not 100%, okay? And now how do we compute the time? Well, we have the same power for heating. Okay, so we are going to use this formula here, but now the time is going to be the power used divided by, the energy used divided by the power. So that's 139,333 divided by 800. And that's, of course, more. It's approximately 174 seconds. So it is slightly more than the time we needed before, 156, because now the efficiency of the heating device is less good. Okay? Does that make sense? It makes sense. Okay. Any questions about this? Sorry, I feel too warm. Okay, now let's continue. And we start a new chapter, which is very close. It's a continuation of what we were doing before. It's heat exchange. Okay. In other words, what we are going to do here is to try to solve this kind of problem. Okay. We have here, let's say, some water. We have a certain quantity of water. Okay, let me see if I use some values. No. So imagine I have 2 kilos of water. I'm giving the quantities in kilos because that's how we need to have them in the equations. We have 2 kilos of water at some initial temperature of 20 degrees. Okay, you have water in a pot. Okay, and let's assume that now we take a piece of something else. It could be, let's say, aluminium. I'm just picking one substance. It could be aluminium, and it could be 0.5 kilograms. I'm just making these numbers up, okay? And it could be at an initial temperature of, say, 500 degrees, because I am taking it from an oven and putting it into the water, okay? So we have one substance at 500 degrees, another one at 20 degrees. We mix them, we put them together, and this is of course done within an isolated system, so we don't lose any heat. And the question is, at what temperature will this stabilize? Okay, so here there is some final temperature for all the substances, because when all the substances are at the same temperature, there is no more heat exchange. Okay, there is always a heat exchange from the warm substance towards the cold substance. But when the substances all have the same temperature, there is no more energy, which is exchanged. You see what I mean? And how should we compute this? The aluminium is going to do what, the aluminium? Let's imagine. Well, no, let's not imagine. The aluminium it's going to give us energy. It's going to give energy to the system, or to take energy from the system. What do you think? Yeah, of course it's going to give energy. It's going to give heat. And how much heat is it going to give? It's going to give a quantity of heat, which is the mass of aluminiums times the C of aluminium, which we need to look up in a table, times the final temperature, which we don't know yet. Okay, we assume there is a final temperature, minus the initial temperature. Okay, and the initial temperature, we know it's 500 degrees. Okay, and the C of the aluminium, I had that somewhere, maybe in the previous pages we had a table with that. Yes, aluminium was 900. Okay, so now the mass of aluminium is 0.5 kilograms. The C of aluminium is 900. The final temperature we don't know, and the initial temperature is 500. Okay, this quantity is going to be positive or negative? What do you think? Negative, yeah? Because the final temperature is going to be lower than 500, And so if the final temperature is 50, 50 minus 500 is minus 450, this quantity here will be negative. The system is giving us energy. Well, let's say more precisely, the aluminium is giving energy to the system. Okay, now what about the water? What is the energy exchanged involved in the water? Well, we have the mass of the water times the C of the water times the final temperature minus the initial temperature of the water. Okay, and the mass of the water is how much? It's 2 kilograms. The C of the water is 4,180. You will soon know it by heart because you will use it a lot. And here we have final temperature minus the initial temperature of the water, of course, which is 20 degrees. And this quantity is going to be positive or negative? Well, the final temperature is going to be higher than 20 degrees, obviously, because the aluminum is going to heat up the water. So this quantity is positive. Okay? And now we need to find an equation to relate these two quantities. How would you relate them, these two quantities? What do you think? Is there a relationship between these two in the system? Hello? Can you repeat it louder, please? Yes, the final is the same, I agree. But what should be the relationship between the two? Think a bit, okay? We have a system which we consider to be isolated. Otherwise, it's a mess, okay? I will explain you in a moment the devices we use for that. It's called a calorimeter. But basically, when you mix two substances and you want to see the heat exchanges between them, you try to do that in a container which is isolated. This is why I drew this kind of line here to show that there is some thermal isolation around it, so we don't lose energy to the outside. Okay, otherwise it's going to mess up the results. But these quantities here, this Q and this Q, okay, which I will call this one, I will call it Q aluminium, and this one I will call it Q water. These two quantities, they should actually be equal to each other, okay? Because all the energy which is given by the aluminium is going to be taken by the water, right? And this transfer of energy from the aluminium to the water will take place as long as there is a temperature difference, and it will stop when there is no more temperature difference, okay? So what we should say in this case, the equation which we should use is the following. Q aluminium plus Q water is equal to 0. Why do I write it like that instead of writing Q aluminium is equal to Q water? Because they have different signs. So if I want these two quantities to compensate each other, I need to sum them up and say that the sum is 0. Okay? Are you following me?
Yes.
Yes. I need some feedback. Okay? Okay, so this equation is what we call the equilibrium equation, but in its very general form, the equilibrium equation should be written like this. This is not general. You can have more than one substance. So the general form of the equilibrium equation is that the quantity of heat which is received by one or more of the substances in the system plus the quantity of heat which is given by the other substances in the system, the sum is 0. Okay? And Q received will be positive, Q given will be negative, and so the sum of these two will be 0. Okay, so if there is more than 2 substances in the system, there will be more than 2 terms in the equation, and it will allow us to determine the final temperature. By the way, can we determine the final temperature in this system? Yes, we can. Let's continue. Let's continue the calculation now. How would you continue it? Let's assume that now, within this problem, I want, sorry, I have my little angle problems. Let's say now that I want to compute the final temperature. Okay? I have everything here. I know that Q aluminium, which is this, plus Q of water, which is this, should be 0. Okay? Let's write it down. Okay, I have 0.5 times 900 times TF minus 500, okay, this, plus 2 times 4180 times TF minus 20, this should be 0. Okay, I just replaced these two guys in the equilibrium equation. Okay, and I got that. And now how do we solve that? Have an idea? Well, we have to isolate TF, but it's a bit of a mess because TF is inside a parenthesis. So what do we do? Wake up! Yeah, we distribute and then we rearrange the terms. Let me first compute these guys because I don't want to take with me all this stuff. So this is 8,360, okay, and this is 450, okay. And so now here this gives me two terms. This gives me 450 TF minus 450 times 500, which I will not compute by the TET, 225,000. Okay, these are these two terms here. And then we have plus 8,360 times TF minus 8,360 times 20. And this is 167,200. And this has to be equal to 0. Okay? And now you have two terms with TF, which we shall keep on the left-hand side. And there are two terms which are just numbers, which we put on the other side. So 8,360 plus 450, that's 8,810. Is that correct? 450 plus 8,360. Yes, that's correct. So we have 8,810 TF, which has to be equal to these two guys that we sum up and put on the other side. Okay, so 225,000 plus 167,200, and that's 392,200. And so finally our TF is going to be 392,200 divided by 8,810, which gives me 44.5 degrees. Aha! Do you think that's possible? Yeah, okay. But what I'm asking is if it's possible. What you said is perfectly correct, but it's a technical point of view. physically, okay, you have the aluminium, which was at 500 degrees and it's going down to 44.5 degrees, and the water, which was at 20 degrees, is going up to 44.5 degrees, okay? So you see that the aluminium is much more, its temperature is going to vary much more than the temperature of the water. And why is that? There are two reasons for that. One of the reasons is what? Remember the C's, okay? The C of the aluminium is 900. The C of the water is 4,180. So it takes a lot of energy to warm up the water. It takes much more energy than to cool down the aluminium, okay? And then we have also more water than aluminium. We have 2 kilos of water, half a kilo of aluminium. So there is 4 times less aluminium, and the constant is about 4 times smaller. 4 times 4, 16. There should be a kind of 16-ish relationship between the temperature differences. I guess it's not that wrong, okay? Yes, it's not that wrong. Okay, you understand? The substances, since their capacity to contain heat is different, the substances, they undergo very different temperature changes when we mix them like that. Okay? Okay, so now let's still see one point, and then we will do a number of problems. I still have to talk to you about calorimeters. Do you know what a calorimeter is? I will show you pictures of a calorimeter. You see my screen now? If I close, you see the plane? Yes? Yes. Okay. So let's see what kind of images we can find on Google about the calorimeter. Well, you have all these images. None of them is a real image, but you can understand. A calorimeter, let's take a simple one. Let's not take the most complicated one we have here. Whatever, they are all complicated, so let's take this one, okay? What is it? It's a device. Oh God. It's a device in which you can control what is going on from the point of view of heat. So it's a device which is isolated, okay? It has this gray layer outside of isolation material. This can be polystyrene, Sagex in French, okay? This can be anything which blocks heat, okay? And then inside this calorimeter, you do some measurement. Here there is a system that is heating up some water, and then you measure maybe how much energy you put in and how much the temperature of water is increasing, okay, and you can measure various things. So a calorimeter is a container which is isolated and which allows you to do measurements. But a calorimeter, it's going to take up some heat because the calorimeter usually has a metallic body. You see here, you see my mouse or not? Hello? You see the mouse, okay. So you see this thing here, which is darker gray, okay. This is probably some metallic or glass container, but this container is inside the calorimeter, and so the container itself is going to take up some heat as we warm up the calorimeter or decrease its temperature, okay. Let's assume there is water inside. Let's assume there is 1 kilo water inside, and I want to increase the temperature by 1 degree. I need 4,180 joules. But if I increase the temperature of the water by 1 degree, I also need to increase the temperature of this internal container, which is maybe made out of glass or out of metal. It's also going to take up some heat, not much, but some. Okay, and this we need to take into account. So every time we have a calorimeter in the game, in the system, every time the system is inside a calorimeter, we need to take into account the quantity of heat which is picked up or given back by the calorimeter, and this will be a new term in the equation. I will show you now. Okay, so there will be a new term in the equation. This is what you can find on page 11. There is a new term of this kind. There is a specific heat which is not like the one before, because this specific heat does not depend on the mass of the calorimeter. This is a specific heat which takes into account the whole calorimeter, and this whole calorimeter it's going to need some energy, okay, like let's say 70 joules per degree, for instance. Okay, that's the value for the calorimeters we have in the classes at André Chavannes. Okay, so this means every time you want to heat up the content of a calorimeter by 1 degree, you need to heat up also the container, okay? And this takes you 70 joules by degree. But it's not by kilograms, because this is accounting for the whole calorimeter, okay? You don't need to weight the calorimeter. It's just given on the calorimeter. And so this specific heat for the calorimeter, this is given in joules per degree, not joules per kilo per degree like the C we had before. And the delta T is in degrees. And so the heat is going to be given in joules. Okay? So when you have a calorimeter, you just have one more term in the equation. We are going to do now a few exercises. We don't have calorimeters in the first ones, which are easy. So I'm now going to ask you to do the first exercise, which is very basic. Okay, you have here it's comparing 1 kilogram of water. No, you are mixing 1 kilogram of water at 70 degrees and 1 kilogram of oil at 10 degrees. And the question is, what is the equilibrium temperature? What do you think? You have water at 70 degrees, oil at 10 degrees. What do you think the temperature is going to be if you mix these two and if they stabilize? You think it's going to be 70 minus 10 divided by 2? You think it's going to be in the middle? Or not? Why not? Speak a bit. Well, it's not going to be the same because the quantity of heat needed by the oil and by the water are not the same. I recall you here that the C of the water is 4,180 joules per kilogram per degree. Okay? Well, do the calculation, or you want us to do this one? Let's do it together. Okay? Okay, let's start. When you start these exercises, start them with the equilibrium condition. Okay? The equilibrium condition is Q received plus Q ceded or given away is equal to 0. That's the equilibrium equation. That's the equation which expresses something extremely deep in physics, which is conservation of energy. Conservation of energy is one of the most basic concepts in physics. Okay, when we have a conservation law in physics, we use it very much because it's something extremely useful. And we have one for energy, we have one for electric charge, etc. And so these are very basic laws. So we start from this, okay? And then we have to write the terms. The Q received is going to be the Q of what? Of the water or of the oil? What do you think? Why the water? What makes you think it's the water? Well, maybe you misread the exercise. The water is at 70 degrees and the oil is at 10 degrees. So sorry? Yeah, okay. The oil is cold, the water is warm, okay? So the oil is going to go from 10 degrees to some final temperature, and the water is going to be from 70 to the same final temperature, because they will have the same final temperature, which we could call the equilibrium temperature. And so the heat which is received is the heat received by the oil, okay? This is the Q of the oil. And is this going to be positive or negative? It's going to be positive because it's received, okay? So the oil, we have the mass of the oil, we have the C of the oil, we have the equilibrium temperature minus the initial temperature of the oil, which is minus 10. Okay? And then the quantity of heat which is ceded or given away, it's the quantity of heat of the water. Okay? The water is going to lose energy and give it to the oil. And so this is going to be the mass of the water, the C of the water, times the equilibrium temperature minus the initial temperature of the water, which is 70. Okay? I don't have enough space for this problem. What did I do when I wrote that? Okay? So now let's write all this. Okay? The mass of the oil is 1 kilogram. Okay? The C of the oil, it's given here. The C of the oil is 1870. And then we have T equilibrium minus 10. Okay? This is obviously positive. While in the second case, we have 1 kilo of water, but now the C of water is 4,180, and here we have TEQ minus 70, and this is of course negative, because TEQ is smaller than 70. Okay? And now, if you don't mind, we continue on the left page. I will continue here, because I don't have space. Okay, now what do we do? Who tells me what to do? How do I solve this problem? Well, it's like before. Now, I need to take these two terms, to sum them up, and impose that the sum is 0. Okay, so I have this term here, which is 1870 times the equilibrium temperature minus 10, and then I add to that 4,180 times equilibrium temperature minus 70, and this should be 0. Okay? And now it's the same as before. So we distribute this, we distribute everything, and we are left with 1,870 plus 4,180 times Tx in the left side on the equation, and on the right side we are going to have 1,870 times 10 plus 4,180 times 70. I give you some time to write down. Are you copying what I'm doing? I guess. Or you're just sitting there and playing PlayStation? No, no, not you. You're a serious class. Okay. So I'm giving you some time to finish that. Okay. Okay. Can I continue? So now we have this equation. I counted the numbers here. So the equilibrium temperature is now going to be 300,300 divided by this guy 6,050, and 6,050, it gives us 51.5 approximately centigrade. Okay? Do you like this result? I'll let you finish writing. Okay? Do you like this result? Does it satisfy you intuitively? Okay? The water, it was at 70 degrees. It came down to 51.5 degrees, which is the equilibrium temperature. The oil, it was at 10 degrees. It came up to 51.5. Aha. So here the delta T for the water is about 9 degrees. Okay. Here the delta T for the oil from 10 to 51 is about 41 degrees. Do you think it's correct? Because of the seas. Because it takes less energy to warm up a quantity of oil than to cool down a certain quantity of water. Plus, I wrote something totally wrong and you didn't even react, which seems to indicate that you are playing PlayStation. From 70 to 51, it's not 9 degrees, it's 19 degrees. Okay, it's 19 degrees. And so you see that there is the temperature difference for the oil is about the double of the temperature difference for the water, and this is consistent with the fact that the C for the water is about the double of the C for the oil. Okay, this is all connected. Okay, isn't that amazing what physics can do? Huh? Okay. Now I let you do the next one. It's very close to the first one, but the first one we did it together. This one you will do it. You will going to do it alone because I'm going to go to a coffee. And now we have 1 kilogram of water at 10 degrees, 2 kilograms of oil at 70 degrees. Do you think? Well, compute and then we will discuss. Okay? You start with the Q received plus Q seeded is equal to 0 equation. You are going to write what your Q received is, what your Q seeded is, and then you put them in the equation and you solve for TF. Okay? I'll let you do that. Hello, hello? Yes. Okay. I'll go do my coffee. I come back. TEQ. Écoute, j'ai hésité à m'arrêter là pour corriger ça, mais je me suis dit, baf, TEQ, TEQ. D'accord? Mais tu peux l'appeler comme tu veux, la température d'équilibre, tu peux l'appeler X si tu veux. Enfin, c'est pas très élégant d'appeler X une température, on n'est pas mathématicien, quoi. Hein? Questions, you can speak, huh? Going well. Okay, are you done? Not yet. Not yet. Okay, so we have time. Somewhere there. Can I start correcting? Okay. So the quantity of heat which is received now by the water. okay, because the water is colder, okay? So it's the mass of the water times the C of the water times the equilibrium temperature. This is EQ, okay, for Aniel, minus the initial temperature of the water, which is 10 degrees, okay? So this we can write as the mass of the water, which is 1 kilograms times 4,180 times TEQ minus 10. Okay. And the energy which is seeded is the energy of the oil, because the oil is warmer, okay? This is Q oil. So it's the mass of the oil times the C of the oil times the equilibrium temperature minus the initial temperature of the oil, 70. So this is 2 times 1,870, which is the C of the oil, minus TEQ, minus 70, right? And so these two terms, we have written them down now. And so we can now put them together into that equation, and then we can solve for TEQ, okay? So we have this term, which is 4,180 TEQ. I'm already doing the distribution, minus 41,800, which is 4,180 times 10, okay? Plus the second term, which is 2 times 1,870 times TEQ minus 2 times 1,870 times 70, and all this should be 0, right? You're still following me? This is what you did probably. And now we have to sum up these two terms. So we have 4,180 plus twice 1,870 times TEQ, which has to be equal to these two terms which we put on the other side and which become positive, 41,800 plus 2 times 1,870 times 70. And now we need to compute all that. So this guy is going to be how much? It's going to be 2 times 1,870 plus 4,180, and that's 7,920, okay? And here we have 2 times 1,870 times 70. This is 261,800 plus 41,800. That's 303,600. And so our TEQ is going to be this number divided by this one. So it's going to be 303,600 divided by 7,920. And this gives us 38.3 degrees. Is this what you found? Okay. So you see that here, okay, one of the substances is at 10 degrees, the other substance is at 70 degrees. The difference between these two is 60 degrees, so the average between the two is going to be at 40 degrees, okay? You have from 10 to 40, you have 30, from 70 to 40, you have minus 30. And you see that the equilibrium temperature now is close to the temperature average. How come? Can you explain me that? Okay, both the water and the oil undergo a temperature change of about 30 degrees. How come it's the same temperature change in this example? in this exercise with respect to the previous one? What would you say? Yes, exactly. Exactly. Did you hear what he said? Okay. The C of the water is about twice the C of the oil. So oil is easier to warm up, but we have 2 kilos of oil. Okay. And so in the end, it takes the same energy to heat up 1 kilo of water as to cool down 2 kilos of oil. Okay. This is why here we get a result which is close to the average temperature between the two substances. Okay. Okay. Let's continue. There are many of these exercises. Then it will become more complicated as we go through state changes. Okay. For the moment, the exercises we do, they should not involve any state change. So if you have a liquid becoming a solid, or a liquid becoming a gas, or a gas becoming a liquid becoming a solid, then you need more terms. You cannot do it with the equations I taught you. But for the moment, we can do it like that. Okay, we will see phase transitions later. Okay, you want to try number 3? Please try number 3. So now you have, well, let's do the drawing. Okay, we have a 10-gram ball of lead. And this ball of lead, this is a different problem. This ball of lead, we let it fall on the ground from a height of 40 meters. Okay, we let it fall. So of course it's going to acquire some energy. I mean, the potential energy the ball has here is going to transform into kinetic energy when the ball touches the ground. And we assume that the energy which the ball has when it hits the ground, this energy, we suppose that it's transformed into heat, and that this heat is taken up by the lead. And the question is, by how many degrees does the lead warm up? Okay, you understand what I mean? Here you have some energy of the lead, which is kinetic energy plus potential energy. But of course, kinetic energy is which value here? 0. Okay, the kinetic energy is 0 because we drop this ball of lead from rest. Okay, down here, the energy of the system is what? It's also formally K plus U, but is one of these 0? U is 0 because we have set the 0 of altitude at the level of the ground. Okay, and so now let me take another color to make it flashy for you. And now this potential energy here is going to transform into kinetic energy during the fall, and then during the shock with the ground, this kinetic energy is going to be transformed into heat. Okay, and this transformation, we assume it has an efficiency of 100%, which is not true, of course, but we assume it has a conversion factor of 100%. Now it's up to you to write the equations which will allow us to solve this problem. Okay, and to decide by how many degrees the lead is heated up. I let you do it. You understand the problem? Hello, hello?
Yes.
Okay, So try to do it. Okay, can we correct it? Allô, allô. Allô, Houston, ici la Lune. Allô. Thank you for being so generous and opening your microphone and letting me know what's going on. Okay, so this problem, you can solve it in one equation if you want. Okay? Basically, let's write energy conservation. We know the U up here, the U is mgh. Now you know that. I'm going to go a bit fast, okay? I'm not going to write mechanical energy, kinetic, potential. Here we have just potential energy, okay? And this potential energy is the mass of the lead times g times the altitude, which is 40 meters. Then this mgh has to be equal to this term down here. The u is 0, so it has to be equal to 1/2 mv squared, where this m is the same m as this one. Okay, it's the mass of the lead, and this is the velocity when it touches the ground. But do we really need to calculate this? No, we don't need, because we know that this is equal to this, and we know that this should be equal to the Q term, to the mass, the same mass of the lead, times the C of the lead, times the temperature increase. We are equating the potential energy, the kinetic energy, and the thermal energy. Okay? And this is not wrong, because when an object hits another object, it arrives with some kinetic energy, and this kinetic energy in a shock is always transformed into heat. There is always some heat involved in a shock, okay? That's why cars start burning when there is an accident, because the accident, the deformation of the structure of the car, causes a temperature increase, and this temperature increase can ignite the fuel in the car. Okay? Now there is one very cute and important thing which happens here, which I would like you to notice. It is that the solution to this problem is independent of the mass of the lead. Indeed, in these equations, this m is always the same. It's the mass of the lead, okay? And so you can simplify it in the equation. The equation no longer depends on the mass, because the more mass you have, the more potential energy you have, but also the more kinetic energy you have and the more thermal energy you have. All these quantities are proportional to the mass, so we can erase the mass. And so if you have a ball of 10 grams, which is falling, or if you have a ball of 10 kilos, the temperature difference inside it is going to be the same. Okay? Good. And now I am going to use one part of this to solve the problem. Here there are three equations. There is this is equal to this is equal to this, and this is equal to this. Okay? I am going to use the equality between these two guys. Okay? I'm going to neglect this because this is an intermediary step and we don't need to compute it. And so now I just have that GH is equal to C lead times delta T. And what I want to know is the temperature increase. Okay? Here it says what is the temperature rise. So this is the delta T. I don't have an initial temperature or a final temperature. I just know the temperature increase, which is given by this. And now I can compute it. It's going to be GH divided by C lead. Okay? GH is what? Is 981 times 40. C lead is 130 or 129, depending on the tables you look at. In this course, we have how much for the lead? We have 130, okay? So the C of the lead is 130. And now, if you do the computation, you get 9.81 times 40, which is 392, divided by 130. This gives you almost exactly 3 degrees of temperature increase. It's not huge, but it's significant. And by the way, but I'm letting you finish to write down and then I will tell you a story. Let me see if I can find some video on internet about that, because no, I don't find anything. I hoped I could find a video in which you see somebody warming up a piece of metal by hitting it. Well, this is one story I've heard. I'm not completely sure this is true, but I have heard that when you work with iron, when you do du fer forgé, I don't know the name in English for fer forgé, I'm sorry. Okay, when you do fer forgé, of course, you can have an oven and warm up your iron. But apparently, you can also warm up your iron just by hitting it. Okay, if you are very strong, you have a nice hammer, and you're not afraid of hurting your hands, you can hit on your piece of metal if it's not too big. Every hit is going to warm it up a bit. And if you hit it like 20, 30 times, then you can make it become warm enough to work on it. Okay? You can make it warm enough for you to deform it, for you to work on the metal as if you had warmed it up on an oven. I should ask one guy who does fer forger if this is true. This is one thing I heard. I'm not completely convinced, but in principle, it's okay. Huh? If you can raise the temperature by 3 degrees with one heat, then 10 heats is 30 degrees. 100 heat is 300 degrees for some metals. It takes you not very far from the fusion temperature. Okay. What do we do with the next one? We do it together or you do it alone and then we correct? What do you want? Answer. We do it together. Okay. Well, you see, the ones who speak is always right. The other ones, they didn't speak, so let's do it together. An aluminium pan of mass 500 grams contains 2 liters of water. Okay, we have an aluminium pan. This is aluminium. Its mass is 500 grams. Immediately write it down in kilograms, so you will have less risk of making mistakes. And this contains 2 liters of water. Okay, here inside we have 2 liters of water, and I wrote 2 kilograms. Then we have a heater of a power of 1500 watts in the bath. So a heater, I mean one of these heaters that you can put in the water like that. Okay, it's basically a heating resistance. You know what I mean? These very basic heaters that you can put into the water, which are very efficient, by the way. Okay. And how much heat should we provide to this pot and water in order to raise their temperature from 15 to 90 degrees? How long do we need to use the heater? Okay. I have to make here an important warning, because from my experience, students make easily the following mistake. Students, they think that every problem we have in thermal physics is of this type. Okay, this is an equilibrium problem. This is a problem in which one part of the system gives heat and the other part of the system absorbs this heat. This is an isolated system. Okay, and this type of problem, when we mix two substances and we look for the equilibrium temperature, this is an equilibrium problem. This problem here, problem 4, is that an equilibrium problem? Of course, if I ask the question with this tone, you know what answer I want. Okay, this is not an equilibrium problem. This is not an equilibrium in which the water and the metal of the pan are going to be mixed, and then they're going to reach a certain final temperature, a certain equilibrium temperature. This is a problem here where we heat up both the water and the pan. Okay, so this has nothing to do with thermal equilibrium. It's not an isolated system because we have energy coming in through the heater. It's a different type of problem. Okay, so be careful when you start solving a problem not to take every problem as an equilibrium problem. Okay? Well, what is going to change here is the signs. Okay? If we consider this as an equilibrium problem, this is wrong, but I'm going to do it. Okay? It would mean that the Q of the water plus the Q of the aluminium are equal to 0. Okay, but now we are heating them up, these guys. Okay, so the Q of the water is positive because you heat the water. Sorry, it's negative because you give energy to the system. So the final temperature is No, it's correct. It's correct. It's correct. Sorry. I'm saying stupid things. So the Q of the water is negative because the fine is. I'm sorry. I'm confused now. The Q of the water, since the final temperature is higher than the initial temperature, is going to be positive, and the Q of the aluminium, it's also going to be positive. Okay, so this equation, you cannot solve it. If you say something positive plus something positive is equal to 0, it means these two guys have to be 0. There is no other possibility. So you can not solve the problem in this way. Okay, but you should solve it in which way? Well, you should compute the quantity of heat which you need to warm up the water and to warm up the aluminium. So every one of them is going to give you one term. Okay, you will need some energy to warm up the water and some energy to warm up the aluminium. And now you compute them. Okay, the Q of the water is the mass of the water times the C of the water times the temperature to this spot and water in order to raise their temperature from 15 to 90 degrees. So they are both initially at 15 degrees and they will both be at 90 degrees because the pan is always going to be at the same temperature as the water. Okay, so in other words, if you want to heat up water for your tea, you also need to heat up the pan, and you will lose some energy to this pan. It's not going to be energy that will be in your water. Okay, so you need to heat the pan. So let's first compute for the water. Final temperature 98 minus initial temperature 15. Okay, this is the energy needed to heat up the water. And then you have the energy needed to warm up the aluminium. It's the mass of aluminium times the C of aluminium times the same temperatures, 98 minus 15. Okay? Ça marche? Are you still there? Yes, you're as silent as in class. Okay, so let's compute now. The mass of the water is 2 kilograms. We have 2 liters. That's 2 kilo. Sorry, I put the unit now. Okay, that's 2 kilograms of water times the C of water times 98 minus 15 plus the mass of the aluminium. It's half a kilo times the C of the aluminium. It was 900 or 800. I'm not sure now. Aluminium 900 times 98 minus 15, and now let's do this calculation. So it's 2 times 4180 plus 450 times 98 minus 15, and that gives me 731,230 joules. I hope I did it correctly. Okay? This is the total energy we need to warm up the system. And now we have a heater which has a power of 1,500 watts. So it's very easy to compute the time we need. Okay, as you know, now we have that the energy, which here we call Q, is produced by some power during some time. So the energy is the power times the time. So the time is the energy we need divided by the power. And so the energy we need is 731,230, and the power is 1,500. And that gives us 487 0.5 approximately. What's the unit here? Unit seconds, of course. And so if you divide this by 60, it gives you 8,12 minutes. Okay. Is that reasonable? 8,12 minutes to warm up 2 kilos of water with a standard heater? Do you think it's correct? Yeah, sounds correct. Okay, you wanted to heat up 2 liters of water for tea, and it takes a few minutes. Okay, 1,500 watts is not a huge energy for a heater. It's an average energy. It's a household heater. It's fine. Okay. So be careful. Some problems are equilibrium problems. Some problems are not. Okay. And you should not automatically apply the equilibrium way of solving problems to any problem, to all the problems. Okay, what about the next one? Is the next one an equilibrium problem? Yes or no? Sorry? Yes. Yes. A moyenne of what? Maybe you can find a way to do it like that, but why do you want to do it? Listen, actually, what we are doing here is une moyenne pondérée. I don't know the word in English. You understand? In moyenne pondérée, when you do an average between different numbers, which each have a different coefficient, because you see here, well, this is not so much in moyenne pondérée. The one which is really looking like in moyenne pondérée, let's go back to this exercise here, which we did before. You remember this exercise? We did it with numbers, okay? And when you do things with numbers, you lose track of the physical quantities, okay? But now let me rewrite this in terms of physical quantities, okay? This was the mass of the water times the C of the water plus the mass of the oil times the C of the oil times T equilibrium, and this is equal to 41,800. That's 4,000. That's, oh God, sorry. Okay, that's now the C of the water times the initial temperature plus the C of the aluminium times the initial temperature. The initial temperature of the water, the initial temperature of the aluminium. Okay? If I rewrite this equation in terms of my physical quantities is this. Okay? And now we can follow what's going on. So the equilibrium temperature is going to be given by CWTI water plus C aluminium Ti aluminium divided by the mass of the water times the C of the water plus the mass of the oil times the C of the oil. And if you wish, this is in some way an average you are calculating, okay? Because Up here you have the C's, and down here you have the C's times the mass. So it's a kind of average of the C's ponderated by the mass, if you see what I mean. Okay, but it's not really an average. While in this last problem we did, yeah, you can consider it as an average if you want. But I see what you want to do, what you are suggesting, but I'm afraid it's going to be more complicated than solving the equation in the way we did it here. Okay? Okay, next one, number 5. Is this an equilibrium problem or not? Read it. Is this an equilibrium? Yes, it is an equilibrium problem because we are in an isolated system consisting of 200 grams of water and an iron vessel. Okay? And so the water, which is at 50 degrees, is going to lose thermal energy to the iron, which is at 20 degrees. Okay? So here, the answer is yes. And we have this Q received plus Q seeded is equal to 0 equation, which is the very basic equation expressing conservation of energy. Okay? You want us to do it together? Why? You want to stop? Oh, yes, it's time to stop. My God. Sorry. Yeah, I didn't realize it's so quiet with your class. Okay, so let's do exercise 5 for next week, which is going to be May 12th. And if you want, you can do also 6. Okay. Anyhow, we are going to do them all, so you can do as many as you want. Okay. Try to make just 2 of them, and we will take it from here. Next time, we will do some more exercises about that, and then we will see how we deal with things when we go from one state of matter to the other. There will be new terms coming in that case. Okay? We stop here. I'm sorry I went a bit longer. You should have told me. But you don't speak, so it's your fault. Okay? Okay, I videotaped the class so you can find it. You will find it on Classroom if you want, if you are interested to watch it again. Okay? I wish you a very nice week, a very nice morning, and see you next week. Okay? Bye-bye. Bye.